steady stream of air can produce sound, sometimes very beautiful sound, sometimes very ugly. Yet sound is a vibration of the air. How can it be produced by a steady air flow? In this film, we study why and how much a flow, even though produced by a constant pressure difference, can generate the pressure fluctuations that we hear as sounds. Sounds that may be amplified by the presence of obstacles in a stream, like this sharp edge. And still more powerfully by the action of resonators, like the pipes of an organ, or the bubbles, whose resonant vibration we shall find causes the babbling of a brook.
A high-speed air jet without resonators can be quite noisy enough. We especially want to study the sound the jet makes, so that aircraft and their engines can be designed to keep ground noise levels within prescribed limits when the correct takeoff procedures are adopted. Also, in the design of rocket launching sites, an important issue is the sound generated again by a flow designed to be as steady as can be achieved. Admittedly, fluctuations are already present in the rocket combustion chamber or the aircraft jet pipe. But jet noise that's extremely comparable if frequencies and intensity are properly scaled on jet diameter can be produced in the laboratory with an air jet, practically devoid of fluctuations in the emerging flow. This raises two questions. First, how do new and quite intense fluctuations arise as the flow emerges into the atmosphere? Secondly, what fraction of their energy radiates away as sound?
The answer to the first question lies in the words flow instability. There's a vortex layer between the jet and the outside atmosphere, and free vortex layers like this can be exceedingly unstable. There's a fast exponential growth of disturbances of a certain type as they travel downstream, so that any small fluctuations present at the orifice, if their frequency is less than a certain value, may have a large positive growth rate and quickly become very big. Now that's an effect of inertia, and it's counteracted by the viscosity of the fluid, mu. The ratio of inertial effects to viscous effects is the important quantity known as Reynolds number. At high Reynolds numbers, disturbances in a wide range of frequencies grow very fast and interact with one another, and we call the result turbulence. At lower Reynolds numbers, the effect of viscosity is to bring this curve down, and then it's only disturbances in quite a modest range of frequencies that have a significant growth rate. So under those circumstances, the disturbances that appear tend to be relatively regular.
We can make them quite regular by an interesting feedback mechanism using an edge and the jet. The flow in this example can be visualized using a dyed jet playing onto a wedge. The wedge casts off an eddy each time the local angle of attack changes sign. The eddy reacts on the nozzle to create a disturbance at the right moment in the cycle, which in turn is amplified by the jet shear. An extremely regular cycle results from this jet-edge interaction. At lower Reynolds numbers, disturbances grow too slowly to be visible close to the jet. But if a loudspeaker introduces artificially disturbances of the right frequency, they quickly grow to something very substantial.
But it is only at these low Reynolds numbers that jets are, in this way, acoustically sensitive. At higher Reynolds numbers, external sound has no influence on the jet. It quickly assumes a turbulent condition because disturbances in a wide range of frequencies grow fast. At the very high Reynolds numbers that arise in engineering applications, the sound of a jet is just a minor byproduct of the turbulence. The turbulence itself is unaffected by its presence.
The wake of a wire in the wind is another free vortex layer, which, like the jet, is extremely unstable. At low Reynolds numbers, round about 100 based on wire diameter, the flow is extremely regular, taking the form of Kalman's vortex streak, which reacts back on the wire, causing it to shed just the right amount of vorticity in each cycle to maintain the streak. At higher Reynolds numbers, more and more frequencies are important, and the flow soon looks quite chaotic.
We've seen, then, that air flowing steadily out of an orifice or blowing steadily past a wire may develop fluctuations. At low Reynolds numbers, regular ones; at high Reynolds numbers, turbulent ones. From this, sound may result in two ways. First, resonators, if present, may be excited by the pressure fluctuations in the flow and may radiate sound rather efficiently. A beer bottle is a so-called Helmholtz resonator, where the inertia of air flowing in and out of the nozzle and the stiffness due to air in the bottle resisting compression define a frequency, and sound radiation is the main loss term. Again, pipes of variable length are used as resonators in musical wind instruments based on the jet edge method of excitation.
But from now on, we shall concentrate on how flow fluctuations, like the turbulence in this jet, generate sound without the action of resonators. How much of the energy of the fluctuations succeeds in escaping as sound? The key word here is escaping. Radiated sound means pressure whose energy propagates away from the source with the sound speed, 350 meters per second. Of course, within the flow, there are other pressure variations, balancing the local fluid acceleration. These do not propagate at all.
Actually, the ear, or a microphone like this, can register these pressure fluctuations exactly as if they were sound. But they are called pseudo-sound. Only pseudo, because they do not propagate like sound. For example, the microphone placed very near the jet registers pressure fluctuations with a minimum each time one of the mixing region eddies passes the microphone and maxima in between. But those are pseudo-sounds because the minima and maxima travel at the speed of the eddies and not at the much larger sound speed. These fluctuations are substantial only very, very close to the jet. You see, if I move the microphone up and down, there are enormous changes in the sound that you hear. Farther out, they disappear altogether. But in this region, we can, with the same microphone, find the real sound if we increase the speed of the jet. But you'll notice that the real sound shows much less variation in amplitude with distance. There is some falling off with distance, actually like the inverse square of distance from the nozzle as the energy is radiated outwards all the time.
To summarize then, At small distances from the orifice, there is an intense level of pressure fluctuation, known as pseudo-sound. Further out, the pressure intensity decays like the inverse square law. Here, the real sound is at a very much reduced level from the pseudo-sound.
The reason why radiated sound is so much less than pseudo-sound emerges after we have looked at mechanisms of sound generation.
The mechanism that generates a simple inverse square law of intensity at all distances is the simple source. We've set up a simple source in this water tank, and we view the shadows of the waves on this screen. We've made the depth of the water to represent sound as well as is possible, in the sense that waves travel at an effectively constant speed. This speed is 20-odd centimeters a second, and propagation from this source is clearly visible, unlike that from sound, which travels at over 1,000 times faster.
Here, pressure fluctuations at a distance r from a sound source vary in inverse proportion to r. That means that the intensity or energy flow obeys an inverse square law. You see that the pressure fluctuations faithfully follow those of the source itself, except for a time lag r over c, which represents the time taken for waves to travel a distance r at the sound speed c. From a source, as its name implies, there's a rate of mass outflow, qt, in grams per second. But it is only rate of change of mass outflow that produces waves. And it is this rate of change, q dot, which is often called the source strength, and which is mimicked by the pressure fluctuations a time r over c later. Any foreign body in a fluid whose volume v pulsates as a function of time acts like a source, and the mass outflow from the body is equal to the density of the fluid times the rate of change of volume of the body, v dot. So, the source strength in that case would be proportional to v double dot. In fact, the waves in our ripple tank are being produced by a foreign body that's being pushed in and out of the water.
A quite different method of sound generation occurs when two equal and opposite sources are close together, and at any one moment the sum of their strength is zero. This contrasts with the field of a single plunger. Although nearby the amplitude of motion is somewhat increased, far less wave energy is propagating away from the source. In fact, you see, in the horizontal direction, contributions from the positive and the negative sources almost cancel.
Those contributions do not cancel exactly in most positions, however, because the distance r from the positive source is not exactly equal to the corresponding distance from the negative source. For example, in a direction that makes an angle theta with the line of length L joining the sources, the difference between those distances is approximately L cosine theta. Now, from that difference in the value of r, we can deduce by differentiating the expression for the simple source field with respect to r we can deduce this expression for the field of the pair of sources. Actually, it's the differences in this r in the denominator that produce this term, and the differences in this time lag r over c that produce this term. Now, notice that at these distances r, which are large compared with the distance L between the sources, the pressure fluctuations depend not separately on the strength Q dot of the sources and on L, but only on their product, Q dot L. The fluctuations are the same as if we had sources that were twice as strong but twice as close together. We call them a dipole sound field of strength Q dot times L.
Now we can see that when L is small enough, the dipole field is going to be very much smaller than the simple source field, which is in fact this part of the expression. This term is smaller than the simple source field by a factor of at least L upon R. The second term depends on the frequency, the ratio Q double dot to Q dot. The frequency over the speed of sound c is a quantity 1 over the wavelength. This term, then, is smaller than the simple source term by the ratio 2 pi L upon lambda. When this ratio is small, we say that the source region is compact. The source field is compact relative to the wavelength. Now, aerodynamic sound at distances r greater than a wavelength or so, the pressure falls off like 1 upon r, like a simple source. Closer to the source region than a wavelength or so, this is the important term. The field is then relatively intense, being induced predominantly by the nearest simple source.
In our ripple tank, there's a local back and forth movement in the neighborhood of the sources. And locked in this local movement, there is a fluctuating momentum. Now, no net momentum can be produced by simple sources, so it follows that in the external dipole field there must be an equal and opposite momentum. We want to know how much it is. And we can find out by considering the mass flow across different disks strung on the axis joining the two sources. We don't know how much that is, but it is obvious that it must drop suddenly by an amount qt at the source where the mass outflow is minus qt, and rise suddenly by qt where at the source where the mass outflow is plus qt. It follows from this that when the two sources come closer to make a dipole, the total momentum in this region between the sources would be equal to this area, so it would be minus qt times this distance L. There must, on the other hand, be an equal and opposite momentum in the external dipole field. And this, therefore, must be plus qt times L. Now, rate of change of momentum equals force. And it follows that the strength of the dipole T L is exactly a force with which the dipole is acting on the external fluid, producing a rate of change of its momentum. Actually, it would be the same not only in magnitude, but also in direction. If we take the direction of the dipole as pointing from the negative towards the positive source. So we can say that a dipole whose strength in magnitude and direction is F is equivalent to the action on the external fluid of a force of exactly the same strength.
Here's a group of sources whose strengths don't add up to zero and they are not in phase. Yet they generate a rather symmetrical wave field. This illustrates the important principle that any group of compact sources radiates like a simple source from some central point if the sum of their strengths is not practically zero. This is because the difference between this arrangement and that arrangement is simply three dipoles composed of the negative source at the center and the positive sources at one of the peripheral points. These dipoles are negligible when the source is compact. The same conclusion would be reached if in addition to the sources there was an externally induced dipole due to the action of a force.
So, in sound generation problems, we always ask first whether the sum of all the source strengths is significantly different from zero. When that is so, then the total source strength is what dominates the external sound field. For example, when a body is changing in shape as well as in volume, we can represent that acoustically by forces distributed round its outside, which correspond to displacements of the surface, and by dipoles corresponding to forces. All those would be important in the near field, but in the far field, it's only the total source strength that matters, and that would depend on the total rate of change of volume of the body, since only that can affect mass outflow.
Thus, in the tank, this irregularly shaped plunger generates a far field close to that of a simple source, essentially because the difference is a sum of dipole far fields that is reduced in magnitude by the factor 2 pi L upon lambda. Similarly, if a bubble in water is vibrating, only its volume change is important in producing sound. These have a characteristic frequency depending on the compressibility of the gas. For air bubbles, these regular vibration of bubble volumes have a frequency of about 600 cycles per second divided by the diameter in centimeters, and makes quite a musical note. Flows of bubbles produce sound mainly because the bubbles are resonators of various frequencies, whose volume fluctuates in response to pressure fluctuations. But here again, pseudo-sound makes itself heard by exciting resonators. A simple source sound field is not so amplified. We see that here, acting underwater. When bubbles are introduced, the sound radiated changes little because a simple source has a far field comparable in intensity to that of its near field, which is exciting the bubble. But a dipole of the same frequency, whose natural far field is weak in relation to its near field, has its radiation greatly amplified when the same lot of bubbles respond to its near field.
But in many important cases of aerodynamic sound, the total force strength is zero because foreign bodies in the fluid are not changing their volume, and the rate of introduction of new fluid is zero, or, as with a jet, practically constant. When this total source strength is zero, this equality remains true, but the second term amounts to nothing. The equality states, therefore, that the whole sound field is equivalent to a sum of dipole wave fields, each corresponding to the action of a force on the fluid. Now, all those effective forces plus any real forces that may be present combine together to form a resultant force. And to a good approximation, the far field is that of a single corresponding dipole. Actually, its strength is equal to the total force exerted on the fluid plus a correction if any bodies are moving through the fluid. This correction is equal to the rate of change of momentum of the fluid supposed to have been displaced by the body. Actually, this correction is often unimportant for air with its low density, but it is used in propeller theory. Each little element of a propeller blade can be represented by a dipole.
We can illustrate this displaced inertia term in the ripple tank. Here we have a solid body vibrating just at the amplitude with which the water moves. It makes no waves, since the force between it and the fluid exactly balances the rate of change of displaced momentum. Now, an identical body is held at rest, which means a much larger fluctuating force, and we observe the dipole field associated with that force, which is what would usually be described as a scattered wave field. Finally, you see both bodies together, one scattering and the other not. The dipole strength for a rod moved rapidly through the air is simply the force with which the rod acts on the fluid. The correction term due to acceleration is unimportant. We can illustrate this motion and the waves it generates in the ripple tank. You see, the dipole axis is normal to the direction of motion. The waves are induced by fluctuations of lift force. At higher Reynolds numbers, as we have already seen, lift fluctuations occur over a broad frequency range. They generate acoustic noise. This is an important part of the sound field of aero engine compressors. Finally, we leave the subject of dipoles by noting that the wind roars mainly owing to the forces with which solid obstacles resist it. Their geometry is very various, and so a broad spectrum usually results.
Here's an experiment to introduce our next main subject. Two rods placed in the ripple tank and vibrated horizontally. They act on the fluid with identical fluctuating forces in phase, and you can clearly see the single dipole field associated with their resultant. Before we switch the phase, look carefully at the strength of the wave shadows in the top left-hand corner. Now, the two rods are being moved in exact antiphase, so that the total dipole strength is 0. And now, the strength of the wave shadows in the top left-hand corner is, as you can see, considerably reduced. This experiment is particularly important because it shows how much smaller the far field is when the resultant total external force on the system is 0. So, when we have air turbulence separated from foreign bodies that can act on the air with forces, we shall get radiation of this type with such a reduced far field. This wave pattern has a name derived from the fact that two equal and opposite dipoles can be thought of as altogether 4 sources. So the combination is called a quadrupole. And you may notice that there are also 4 directions in which its far field is strongest.
We've seen earlier that the field of a dipole is smaller than that of an individual source by this factor 2 pi L upon lambda, because two sources opposing each other, separated by a small length L, which is small compared to the wavelength over 2 pi, almost cancel. Now, a quadrupole has two dipoles opposing each other. So again, we repeat this cancellation factor, and we get 2 pi upon lambda squared for the efficiency of the quadrupole versus the individual source. A common example of the quadrupole is the tuning fork, where the two tines vibrate in antiphase, inducing equal and opposite forces. Much less energy is heard now than when we baffle one of the tines to hear the field of one of the elementary sources.
These ideas explain why, in a turbulent jet, the pseudo-sound or near-field pressure fluctuations are so large in relation to the radiated sound or far-field pressure fluctuations. There is no variable rate of introduction of new fluid, so total source strength is zero. There is no force exerted on the fluid by any foreign body, so total dipole strength is zero. Therefore, we can say that the radiation is of quadrupole type, and far-field pressures to near-field pressures are not simply in the ratio L over R as for a source, but carry the additional factor 2 pi L over lambda squared.
We see already why it is so difficult to reduce the sound of a jet. Any idea that the turbulence in the jet may be modified by inserting solid obstacles will fail. This is because the solid obstacles induce a dipole field, much more efficient than the quadrupoles which are in the jet alone.
We can calculate the strengths of the quadrupoles. We use the fact that the main difference between laws governing how velocity components fluctuate in a turbulent jet and in a simple acoustic medium is that momentum transfer in and out of a fluid element is not accomplished simply by pressure. There is additional transport of, for example, this component of fluid momentum, rho u, by these motions at right angles. The resulting momentum transport, rho u v, can be thought of as a force with which the fluid element acts on the external medium. It consists of two equal and opposing forces, so it is effectively a quadrupole. Actually, the quadrupole strength per unit volume for quadrupoles of this orientation may be proved to be rho uv.
This, then, is the quadrupole strength per unit volume. But what volume does a single quadrupole occupy? The answer lies in the statistical nature of turbulent fluctuations. There is a tremendous interference between waves generated from uncorrelated regions. But from any small region in which the fluctuations are well correlated, the waves are relatively well ordered. This suggests viewing the turbulence as made up of distinct elements of scale L within which fluctuations are well correlated. Contributions between two regions in different regions are uncorrelated. Actually, pressure amplitudes from regions in which the correlation is high add linearly, but the mean square pressures add linearly from uncorrelated regions. Measurements in the jet show that correlated regions, or eddy, look something like this. Measurements also show that the ratio 2 pi L upon lambda is of the order of the fluctuating velocity in the turbulence divided by the speed of sound, so that in low-speed jets this ratio is very small.
This general formula for quadrupole radiation can be used to estimate the total sound output from a jet at speed u. For modest speeds, 2 pi L over lambda is about 1/7 of u over c, because the fluctuating velocities just referred to are about 1/7 of the jet's speed. So this whole factor is about the square of the speed measured on a scale of 7 times the atmospheric sound speed. But the near-field pressures themselves vary like u squared, so the far-field pressures go like u to the 4th, and the intensity of sound radiation, therefore, like u to the 8th. Now, that rather crude argument gives a result in surprisingly good agreement with measurements of total acoustic power output for the more moderate values of the jet speed. But there are 2 corrections that we need to make to it in order to understand noise at the higher jet speeds. First, net turbulence production tends to be somewhat reduced at the higher Mach numbers, which tends to raise the value of this numerical factor. That would make power output increase somewhat more slowly at the speeds round about u over c equals 1, more like a u to the 6th law. But the second correction works the other way and restores the u to the 8th dependence up to a value of jet speed around 1.5 times the atmospheric sound speed.
This second correction is due to the fact that the turbulent eddies are moving at about half the jet speed relative to the atmosphere into which they radiate. Now, the best-known property of moving sound sources is the Doppler effect, whereby sound coming towards us seems to have a higher pitch than the same sound going away from us. We can illustrate this in the ripple tank. You see the wavelength ahead of the source is reduced, that behind the source increased.
If an eddy is moving with speed ue, then the wavelength of sound emitted forward is reduced by a factor 1 minus ue over c, essentially because during the time between emission of crests, the sound has traveled a distance lambda, while the eddy has moved on a distance ue over c times lambda. For emission in other directions, making an angle theta with the direction of motion of the eddy, the same argument applies with ue replaced by the component ue cos theta in that direction. So the wavelength in that case is 1 minus ue cos theta over c times lambda.
This eddy Doppler factor changes the compactness ratio. 2 pi L upon lambda becomes 2 pi L upon lambda divided by the Doppler factor. This now is not so small in the forward direction. So we see here a tendency for a preferential forward emission. This is at its extreme in the so-called Mach wave direction of supersonically moving eddies. Then ue upon c times cosine theta is equal to 1, and the wavelength evidently reduces without limit. Then there can be no quadrupole cancellation, and the sound is simply simple source. It's as if the eddy were moving, generating its own sonic bang. Here we have a shadowgraph picture showing that the sound field of a properly expanded supersonic jet is simply a collection of Mach waves. We can illustrate this in the ripple tank and follow the development of these waves. At high speed, then, we have important consequences coming from the breakdown of this compactness condition. The sound is then directional and simple source, the pressure falling off like L upon R from the turbulence, all the way from the turbulence, where it varies like u squared. The mean square pressure then varies like u to the 4th.
Detailed arguments on these lines show that the high-speed form of this curve follows a u cubed law. The transition occurs about u over c equals 2, where the eddies first become supersonic. This agrees rather well with the observations. Another way of plotting the results is in terms of the acoustic efficiency, which is acoustic power output divided by jet power. And you see that at modest values of the jet speed, this takes quite low values, around 10 to the minus 5. But at the higher speeds, when the supersonic bang mode takes over, the curve levels off to just under 10 to the minus 2, essentially because inefficient quadrupole radiation has become replaced by efficient simple source radiation. More detailed study of data in various frequency bands confirms the view of a turbulent jet as exciting the external acoustic medium in the same way as would clusters of eddy-sized quadrupoles that are traveling in the direction of the jet and whose strength reflects turbulent fluctuations in momentum transport.
Of course, jet engine powers have consistently increased, while at the same time there's been an incentive to get the acoustic power down as far as possible. This has attracted engineers to come ever further down this curve with turbofan engines at low jet velocities, achieving their increased power with large jet diameters. The turbofan was attractive for many reasons, of course, but one of the most compelling was the noise argument. This could at best be a long-term solution, however, so other means of jet noise reduction have been vigorously sought. This was difficult, but nonetheless, important improvements have been achieved using devices which, for given jet speed, reduce this ratio, 2 pi L upon lambda, by reducing the turbulent intensity.
The idea is to get the external atmospheric air moving in the same direction as the jet gases so as to reduce the total shear that is producing those turbulent fluctuations. This design of jet exit does this and has a second important advantage in that the annoyingly intense directional peak from any one of those small jets gets flattened because its sound gets scattered by the presence of all the other jets. More recent research on aircraft noise reduction has concentrated on compressor noise, which we mentioned earlier and which has become relatively more important for the big turbofan engines. But that's only one of several fascinating contemporary applications of the basic knowledge that we've outlined on aerodynamic sound generation.